Okay, so I thought that I would do a little supplement lecture here to sort of follow up on the one that we did um, last we met on Wednesday, which was we were doing this controller design. It was a PI controller, the first one that we did. We started with P, and then we added I, and then we can also add D, and so we can have a PID controller. The design using pidtune is what I want to focus on today for just a short while. So the idea is that instead of having to do all of this manual design, which isn't so bad really, but we can have MATLAB tune it for us. So PID controllers have three parameters that we can adjust, adjustable parameters. So what I want to do in this little short lecture is to show you how to use pidtune to build a PID controller, and yeah, so that you guys will be able to do that if you're unfamiliar. So let's remember what we did so far first. So we have this script that defines the open loop transfer function G. We used the root locus to find a gain that we thought was appropriate using just proportional control to do some transient response design. And we closed the loop using this feedback function. And then we did a step response simulation for the closed loop system. So we changed the reference from 0 to 1, and we wanted to see what happened. And that looked, well, we'll run it, and I'll show you. So I'll do cell by cell, just so that we don't see everything at once. There was the root locus, and then we closed the loop, and then we did this step response, and we didn't plot it actually at this point, so I'll open up a figure, and we'll plot TA Y step P, and we got this response, and we proceeded then to add integral compensation because the steady state response was at 0.6 something instead of 1, which it should be. If our reference is 1, the output should be 1 if our controller has 0 steady state error. And in this case, it has significant steady state error. So we added a compensator, integral compensator, and we adjusted the gain appropriately to get an appropriate controller design here. So we did a new root locus. We simulated then what happened for our PI controller, and we got pretty good. So that, remember, it was first to start off pretty slow. We moved the 0 around, and we made it better. So yeah, this was our final design. Not too bad. So what we're gonna do is we're gonna do now a PID in addition, but we'll use pidtune to do that. Also, notice how we're simulating kind of a lot of extra time here that we don't really need to anymore. So let's like lop this off at like 2 seconds because it's kind of a lot of extra there. So like 2 seconds. Great. And we also did this sinusoidal ramp reference just to see if we did a different ramp, or did a different reference. What would the response look like? We could simulate that. So we did that using LSIM. That's neither here nor there in terms of the controller design, but this is our P and our PI controller. So let's do a PID now. So if we want to use pidtune, so let's take a look at the docs for pidtune. And so we have a PID tuning algorithm for linear plant model. So there's a lot in this documentation, and there are a lot of interesting different types of controllers that one can do. But the sort of simplest way to march through this is to just hand it a system, an open loop plant, just a plant, and then tell it what type of controller you want to design. We'll have it design a PID controller with this additional filter. So PIDF is what we want from MATLAB. So notice that PIDF is one of the types that we can choose. So PID controller with first order filter on derivative terms, which makes it a little bit less susceptible to noise. And that's what we desire for the controller in Lab 8. So and then it'll choose the gains for us. It's going to just move those around until it thinks that this is a good set of gains. The kind of things that it's trying to play off are transient response. So it's trying to get a pretty reasonable transient response. And it's also trying to have a significant amount of phase margin. So usually you're sort of trading off between those two. And phase margin has to do with robustness, so gain margin, phase margin, our metrics of robustness. And in this class we didn't talk about that, but if you've been in a class that had more control involved in it, you would know that robustness has to do with like if the parameters of the system changed at all. So if you had like a plant that changed maybe one of its parameters 10%, would your controller still perform okay? Would it have similar transient response, or would it go completely unstable? And that's actually specifically the metric that we're most concerned about, is if you change the parameters of the system, how much can you do that without causing the system to go unstable? So if you're right on the edge of stability, and then one of the parameters in your system changes a little bit, you're not very robust, because if you're just barely stable, and if you change a parameter in the system just slightly and you go unstable, it's not very robust. So it's making sure that it's balancing gain, phase margin, so robustness, with the transient response characteristics that you would probably want. So you can specify that to some extent with some of the options, but I'm not going to go into those details. So let's just use it in a sort of naive way. We'll just use PIDF, and we'll give it our open loop controller, and we'll just see what it designs for us. And it's going to be interesting because I actually don't know. I've not actually tried this. This was a system I just made up, remember? So instead of having to do like use the root locus and choose the gain associated with a certain percent overshoot or rise time or something like that, we're just going to hand the system to this this function. So the syntax is pidtune, hand the system, the type, and it'll return a controller transfer function object for you. So you can then use that to simulate an LSIM or step, as we will do. So let's call this C. Did I call anything else? I call them CI. Okay, so C. I'll do PID. There's the PID controller, and so we'll just do pidtune. We'll give it our open loop controller, our open loop system. Actually, I should be more precise. Our plant. So there's our plant. And we're not putting any of the compensators in that we've designed previously because we want it to be independent of those. So we just give it the original plant. And we tell it to do PIDF, so that filtered PID controller. And that should return to us. Well, actually, we'll look and see, like, what is the object that it returns? So what does it print for us? It prints for us, it says, here's what it is. It's a PID controller. KP, KI, and KD are the PID gains. And it's using KP, KI, and KD as it specifies here. That was how it tuned it. It tuned it to those specific gains they said for this plant, these gains will be good gains. And then TF has to do with the frequency at which we have cutoff, right? So when we have our typically our, so this is our proportional term, this is our integral term, that all looks normal. Our derivative term, though, has this a pole in it. So it's not just S, it's also got this pole. And that pole has cutoff frequency. So that pole is going to be this high low pass filter, and the cutoff frequency is going to be associated with 1 over TF here. So this is our time constant of that filter. So chose that to be here, which once again it's choosing based on the system, the plant, and how it expects you would want the system to perform. It's a good place to start for designs. So we're just going to use it naively and go from there. So this is our controller. And if we would like to know what happens in closed loop then with this controller, we would need to do just like before, we would do G closed loop PID feedback. You give it the forward transfer function first, so that's going to be C PID times V plant, G. And then the feedback we're going to say is unity feedback. So this should be our closed loop transfer function with the PID controller. And what we'd like to do is find the step response. And in fact, we want to do, see, evaluating settling time via step info. So settling time, we should probably do this too. This is all stuff that has to do with all three of them. So I'm going to actually move the step simulation to the bottom. We did it before. And I'll also move the step info to the bottom as well, because we aren't so much interested to do this like all over again. Let's just add another line to it. So G closed loop PI, let's add, so we have the PID. So then we have Y step PI. Let's also do Y step PID. So this will do a step response simulation for us, and it'll give us Y step PID, which is the one for the PID controller. We already were plotting our responses here for P and PI controllers. Let's also plot it for the PID controller, and let's add a line to the legend, PID control. Well, and in fact, we could put the F on there if we want to, PIDF control. And then we evaluated the step responses, and we printed out what the settling time was for these others. So let's do that for this as well. So PID settling time. Okay, so I think we got it all in there. Let's give it a shot. Oh, undefined function or variable. Yeah. Oh, it's because I did the sinusoidal ramp thing. I'm just going to comment this out for now. This really should go up. No, I'm going to share this with you guys, so I don't want to forget to uncomment it. So put it at the very bottom. After all of our controller design stuff. The sinusoidal ramp reference was just sort of a playing thing that we did, so I'll still leave it at the bottom, but that's not really the focus of what we're doing here. So this is that. Alright, so here we have our P, PI, and PIDF control responses. This is not very thick, so I want to do... I want to increase it a little bit because that yellow is a little hard to see. So here we go. We have our step responses. remember with the P control, we had this big steady state error. The PI control, we got rid of that steady state error, and our performance was pretty good. We increased the gain, so more control effort to make this happen, but it looks good too. Our PIDF controller, it has a pretty nice transient response. Notice that it's not really focused on a certain settling time. I think we designed the previous settling time for 1 second, but when we asked this controller, this MATLAB script, we didn't tell it what settling time we wanted. So it didn't know. It just chose something that it thought was pretty good. So 1.11 seconds is what it is if you actually evaluate the numerical data. However, you can see it just takes a little longer to settle. The percent overshoot is pretty minimal. I think that it looks like it designed it for about 5% overshoot, which is, pretty nice, but we were doing about 23% before, so it's sort of a different transient response, right? Similar rise times, not significantly different on rise time. But yeah, settling time is definitely longer, and and also the percent overshoot's a lot smaller, which may or may not be what we want. So there's not as much flexibility, and you can tweak some things in this pidtune, and I do encourage you to play around with it. But in the lab, we're not getting into the details of how to use or master pidtune. So we're just kind of using it naively in the way that whatever MATLAB thinks is about right, which gives you a reasonable one. And even in this case that I totally made up, it worked pretty well. It was pretty close to what we were going for. So it isn't great if you're going to try to go for a very specific design criteria, but gives you a pretty reasonable controller for a lot of cases. So that was the sort of pidtune tutorial. So I hope you enjoyed that. I will upload this source code to the website so you have that. All right. Have a good last week of classes. See you guys on Wednesday.